Okay, this is David Zierler, Director of the Caltech Heritage Project. It's Tuesday, June 28th, 2022. I am very happy to be here with Dr. Wayne Thatcher. Wayne, it's very good to be with you. Thank you so much for joining me today.
My pleasure.
Wayne, to start, would you please tell me your current or most recent title and institutional affiliation?
Research geophysicist, Earthquake Science Center, U.S. Geological Survey in Menlo Park, California.
Wayne, how long were you with the USGS?
Well, I passed 50 years at the USGS last fall.
Oh my goodness. Was there some event marking the ceremony?
No, not really. We're pretty informal about that at the USGS. Everyone knows, and we're family, no big deal.
Of course, it was the pandemic as well to put a damper on things.
Yeah, probably. I'm sure that I will get my 50-year government service pin sometime in the next year, and maybe there'll be a little bit of a hoo-ha about that.
Wayne, just as a snapshot in time, what are you currently working on? What's interesting to you?
Well, my interests in earthquakes and seismology and earth sciences in general they were born in Southern California when I was a Caltech student, and the project that I've been working on over the last several years involves trying to improve estimates of the temperature structure of the sphere under Southern California, which strongly influences the way Southern California deforms and the way earthquakes occur.
Wayne, over the course of your career, what aspects of your research have been more on the observational side and what are more on the theoretical side?
I'm basically an observationalist. I use the kinds of observations that seem to me to suggest new and exciting avenues for research, and then I follow those up as diligently as I can, using theory that others have developed for the most part, although I've done a little bit of theoretical research myself.
What are some of the theories in seismology or geophysics that have been most important in your observational work?
After the Great California Earthquake of 1906, or sometimes called the San Francisco Earthquake, a very eminent physicist, basically, named Harry Reid, promulgated a theory called the elastic rebound theory, which basically said that stresses build up slowly in the earth around earthquake faults by elastic processes, and then when the strength of the earthquake faults is breached, then an earthquake occurs and the strain is released. That's a very central idea that certainly informed my early research, especially after my PhD.
Wayne, being at the USGS for your career, in what ways did you pursue research questions that might have been different or unique had you been at a university or another academic institution?
That's a really good question, David. First of all, and for much of the first decade and more of my career, I had the freedom to choose whatever research interest topic I had in the broad field of earthquake science. Over time, I began to appreciate that the USGS did have a niche in earthquake science that was a little bit different than the academic one, and that was to do research that contributed towards not only understanding fundamental processes, but affecting society and social decisions about, for example, building codes for making California's structures safe, and making long-term assessments of hazard that were important for setting earthquake insurance rates and zoning for earthquake hazards.
Wayne, what have been some of the key technological advances in the field that have been most relevant for your research and the kinds of questions you've pursued?
Oh, really terrific question. Uh, like anyone who's done science over the last 50 years, the development of computational capabilities due to the inexorability of Moore's law have had a very important impact. Uh, my research, probably from the time 3 or 4 years after I got my PhD, has been more directed towards um, measuring and interpreting the motions of the Earth's surface around earthquake faults and volcanoes. And in that research, the global positioning system and satellite methods of imaging the Earth's surface have become increasingly important in ways that I never would have forecast in the 1970s when I turned my attention to this particular field, this specialty.
Wayne, tell me about your use of old earthquake data, even from the early 20th century. How have you applied that in a more contemporary context?
Another good question. Soon after I came to work at the U.S. Geological Survey, I became fascinated by the great 1906 California earthquake, which ruptured over 450 kilometers of the San Andreas Fault in Northern California. And there were two unique sources of data that hadn't been sufficiently exploited. One was the old seismograms from that earthquake, which are collected in a particular study and published volume on the 1906 earthquake. And the second was historical geodetic measurements of the relative displacement of survey points around the San Andreas Fault before, during, and after the 1906 earthquake. Those data had previously been unexploited, and I was able to use some modern methods to reanalyze those.
Is there a threshold in earthquake size or magnitude by which you decide whether or not to study a particular quake?
Not really. I mean, the biggest earthquakes are the sexiest, and so certainly my attention and everybody else's is usually drawn to them. But tiny earthquakes can teach us a tremendous amount about the Earth, and even what are called slow and silent earthquakes, which have been discovered over the last 20 or 30 years, have really revolutionized our understanding of earthquake processes.
What have been some of the biggest surprises in the field since you've been at the Seismo Lab?
Well, first of all, plate tectonics. When I entered grad school, plate tectonics and continental drift were mostly considered heretical ideas that were probably wrong. Within a period of a few years, the entire field, pretty much in Earth sciences generally and seismology in particular, was totally persuaded that that was the way the Earth works.
Would you say that there are orthodoxies in the field from the time you were a graduate student that have been totally overturned at this point?
Well, first of all, what I just mentioned, plate tectonics, certainly changed, everything in earth sciences and certainly in seismology. Since then, I guess I don't have an immediate response other than to say that the implications of global plate tectonics for seismology, these continue to be explored and exploited. That's something that has produced a number of surprises over the decades. These slow and silent earthquakes that I mentioned, the recognition that earthquake processes from sort of very long periods, like those that are measured geodetically, to the very highest frequencies, hundreds of hertz, are all part of the same process and are interrelated in continually fascinating ways.
Wayne, has field work been important in your research? In other words, are you compelled to go out to a site when there's a particular set of questions to pursue?
Yes. The first of all, in the early 1980s, with the development of global positioning system technology, it took about 5 years for enough GPS satellites to be in orbit around the Earth to be able to measure positions and changes in positions on the Earth's surface to sufficient precision to be important for understanding earthquake processes. In the early 1990s, this came to fruition, and for almost 25 years, I went to the field every year to make these GPS measurements around earthquake faults all over the western United States, as well as in other parts of the world with colleagues. And it's been one of the most enjoyable and satisfying parts of my career to be in the field, making measurements that will, whatever theories or speculations I come up with, the observations themselves have great merit, and that was very satisfying to me.
Wayne, in analyzing data, whether on-site or coming to you remotely, when is it possible to extrapolate from a particular site and make more global observations, and when is it really site-specific in terms of understanding what's happening?
Terrific question. That's the challenge of being a geologist, an earth scientist. We nearly always, whether we're mapping some area as a field geologist or we're studying a particular earthquake in California or elsewhere, I think we're all mindful of trying to understand if our particular observations, our earthquake or our geological field study area, what we observe there has general implications for Earth processes, and it's kind of an art to try and figure this out and be able to make generalizations that will be appropriate and stand the test of time. The Earth is very complicated.
Wayne, going back to the idea that at the USGS you were free to pursue your own research interests, how do you square that circle in terms of being funded by the taxpayer and presumably having some mandate to serve the public good?
Well, when I'm ambitious and full of myself, I thought that anything that I would do would contribute to the betterment of the world and the United States and the USGS. As I mentioned, over time, I realized that the USGS has a special and distinct mission, and so my research was naturally influenced by that. That said, just about everything that I did and that was done at the USGS contributed to understanding earthquakes better and thus understanding their hazards and the implications for society.
As a member of the USGS, have you been largely unconstrained in terms of funding? In other words, professors in academia always need to find federal support for funding, but as a federal employee, was this not a concern for you?
Oh, it was a concern, certainly. About 10 or 12 years into my career at the U.S. Geological Survey, I took on a job as a science administrator for 5 years. I was responsible for about 80 other PhD level scientists, a program that was, I forget exactly, $15 or $20 million a year at that time. And so I was keenly aware that I had to justify the work that was done in my group to the people at higher levels in the USGS who argue for funding through their interactions with.
Wayne, I've come to appreciate some of the great debates about whether earthquakes can be predictable at some point. Where do you fall in those debates?
Um, well, I guess I wish we could predict earthquakes. Uh, so far, uh, there's there has been no convincing evidence that we will be able to predict the time, place, and magnitude of earthquakes. That said, I've found throughout my scientific career there have been surprises. Over the last decade, new technology, in particular the global positioning system results, have suggested that for some earthquakes there may be precursory movements of the Earth's crust that are able to forecast at least some of the largest earthquakes in a general way. But earthquake prediction is a dream, not a reality.
Wayne, it's as much a philosophical as it is a scientific question. The fact that we can't yet predict earthquakes and might not ever be able to what extent is that a statement about the limitations of our technology? And to what extent is it simply the Earth itself doesn't know when an earthquake might happen?
Well, the answer to that question is I don't know the answer to that question.
What does your gut tell you?
I think I'm enough of a scientist that I would not trust my gut to tell me one way or another. As I said, throughout my career, I've always been surprised by new observations, often as not driven by new technology as much or more than new ideas. And we can't predict what technological developments will occur in the next 50 years any better than we were able to predict them for the last 50 years.
Wayne, if not predictable, what about the idea that earthquakes, at least on the century or 1,000-year scale, are cyclical?
Again, that's a great question, and it seems as though some earthquakes are and some earthquakes aren't cyclical. The degree to which they're cyclical is, even in the best documented cases, imperfect. So, for example, in southwestern Japan, large earthquakes, great earthquakes, occur roughly every 100 years, and it's been about 80 years since the last large earthquakes in that region. And Japanese seismologists who understand their turf probably better than any other part of the world, with the possible exception of California, are divided on how likely a great earthquake would be in that region in the next 20 to 40 years. So once again, the Earth is complex, and it's not. If it's a physics experiment, it's a physics experiment with very many variables.
Wayne, in all of the kinds of earthquakes you've studied, either by citing specific examples or generally looking at their characteristics, are there certain earthquakes that are simply more demonstrative, that teach us more about geophysics and seismology?
Again, that's a great question. I would say the largest earthquakes, the great and giant earthquakes, like the one that occurred off the coast of Japan in 2011, the one in Sumatra in 2001, I guess. Those are the earthquakes that have the greatest impact on our thinking, on our ideas, and on our understanding of earthquake processes.
The theme so far has emphasized what we don't understand. What about some of the things that we really do understand much better than at the time when you were in graduate school?
Oh, so many things, David. On the practical side, we know much more about the character, the magnitude, and the effect of earthquakes particularly of strong ground motion, and their effect on the built environment. When I was a grad student, no one believed that ground accelerations would ever exceed 1g, or the force of gravity, and many thought that it was much less than 1g, based on what observations existed at the time. Now we know, and many structural engineers would poo-poo any evidence that seismologists would provide that ground motions are significantly stronger than had been designed for in the construction of earthquake-resistant buildings. We know that that's not true now. We have expectations and knowledge on what the largest ground motions are likely to be, and working together with engineers, it's possible to make better assessments, both in constructing new buildings to be earthquake resistant, and in assessing which are the dangerous or hazardous buildings that over time should be phased out of the building inventory.
Wayne, have you been involved in earthquake early warning at all?
I have not. I've been a very interested spectator. The USGS has probably the lead mandate in trying to understand the degree to which we can actually do effective early warnings, and then how to implement it in practice.
Wayne, some technical nomenclature questions as they've been relevant in your career. First, what is strain accumulation?
The best way to understand that is to imagine the inexorable motions of the Earth's great tectonic plates. In our neck of the woods here in California, the Pacific plate on the one side is moving to the northwest towards Alaska and Japan, and the North American plate is moving roughly southeastward. And the San Andreas Fault is one of the main plate boundary faults, and it's in between large earthquakes. It's stuck. It's not slipping, but the plates are moving on inexorably, and so you can imagine the Earth's surface being deformed because the plates are moving in their inexorable way. But the San Andreas Fault, the main boundary, is stuck.
The term megathrusts, is that to suggest that there's a sliding scale of thrusts and that's the largest?
No. Well, in a way, but usually that refers to the places where the great oceanic plates dive down into the Earth's mantle at subduction zones, and at that point, the boundary is an inclined fault where one side, usually the continental side, wants to move upward, and the downgoing plate wants to slide downward, and so the shallowly dipping surface of that plate boundary is called a megathrust.
Wayne, the term viscoelastic, in the context of seismology, what does that mean?
It means that below about a depth of roughly 70 kilometers, no, I'm sorry, I take that back. Below a depth of about 15 kilometers, the actual material behavior of the Earth's lower crust and upper mantle is different from that in the upper 15 kilometers, in that when an earthquake occurs, there'll be an instantaneous change in the stresses below 15 kilometers that will slowly relax with time in a somewhat viscous way. Silly putty is kind of an example where if you pull on it quickly, it'll snap and break. But if you pull on it slowly, it will slowly deform. And that viscoelastic response of the Earth's materials below about 15 or 20 kilometers is very important for understanding both the release and the buildup of stresses, this strain accumulation and release cycle that we talked about earlier.
Wayne, either conceptually or observationally, how did you develop the boundary between what you called the thin and the thick lithosphere?
Oh, that's part of my research that John Vidali might have referred to.
That's right.
Well, it was basically incorporating ideas from that or implications that were required by plate tectonics to the idea of the occurrence of great earthquakes like the 1906 San Francisco earthquake that I mentioned. One of the earliest, what's the right word? Things I'm proud of in my career was the work that I did in the 1906 earthquake, which suggested that these slow movements that occurred and that I was able to extract from data after the earthquake, these slow movements that were aseismic were related to these non-elastic processes that were occurring at the deeper levels of the Earth's crust. At the same time, laboratory rock mechanics experiments were revealing differences between the behavior at the level where earthquakes occur, where the processes are mostly elastic and produce sudden fault slip and then elastic buildup and release of stresses, was different from that in the deeper regions where the materials were hotter and they tended to flow rather than snap and slip in earthquakes.
Wayne, it's known that you were early adopting of space-based geodetic methods. I wonder if you can explain visually, what did you appreciate about the value of looking from outer space when the processes that were happening were essentially subterranean?
Another great question. I think I, like many other geophysicists, were actually astonished to discover that engineers and space scientists were developing a method that allowed us to be able to measure distances or the positions of points within millimeters from a satellite that's 800 kilometers in the sky and moving at 5 kilometers a second. It seemed mind-boggling that this was possible, but it was early demonstrated, especially at my agency by colleagues of mine, that this indeed was true, that by us being very careful in our observations, observing for a long time periods to cut down on signal to noise, that we could actually measure this. And since I had previously worked on using classical geodetic methods, I really could understand how revolutionary these new capabilities were, and be one of the early ones to adopt them and actually go out and make measurements in the field.
Wayne, did you envision satellite imaging to work in concert with land and underground sensors, or were they an independent instrument?
Well, I saw them as part of the whole spectrum, from very very long periods, geodetic scale, years, months, decades, to be a continuum with the measurements that we make with seismographs on seismograms, because that was my training. I was trained as a seismologist, but my interests at the USGS quickly took me elsewhere. So I saw them as part of a whole.
Wayne, from your earliest notions of the thin versus thick lithosphere, how has that changed conceptually over time?
Another terrific question. I think broadly speaking, uh, we think that both are valid, and it just depends on the time scale. At the time scale of the occurrence of earthquakes, the thick lithosphere model is appropriate because the behavior of Earth materials is largely elastic over those time scales. Over longer and longer time intervals, years, decades, centuries, there's no doubt that the thin lithosphere model is appropriate. So, they're kind of both right. We still argue about details about where this boundary is between the thick and the thin lithosphere models. But I think there's pretty much general agreement that both conceptual models are appropriate depending on the process and the time scale you're considering.
Wayne, one more question as it relates to an overview of your career, and that's one relating to style. When in your research are you so confident that you've made claims or arguments boldly? And when do you feel it's most important to hedge your bets or be more humble about what you're seeing?
Well, this may be saying more about the difference between youth and maturity, but for me, I was always bold when I was younger, and I'm much more measured and cautious at this point in my life.
What's the big story there? What does the benefit of maturity tell you as you reflect on these things?
Oh, each has its own age. I sometimes cringe at my boldness when I was young, but it had its advantages. I pursued my passion and my interests with great diligence and enthusiasm, and worked my butt off because I was so sure that I was right. And now there's certain advantages to having what's the right word? A more accurate perspective on the way things are, both in science and in life.
Wayne, in thinking about these things in generational terms, at the USGS, are there opportunities to serve in a mentor capacity with more early career scientists?
Oh yes, one of the great satisfactions of my my more mature years is working with younger scientists, both from the energy and enthusiasm and idealism that they imbue, which I admire and respect, and also in the sense of being a mentor and being able to endeavor gently to pass on what I think I've learned that will be of value to young scientists as they grow into themselves.
Wayne, now let's go back to the pre-Caltech years. Where did you do your undergraduate?
I was born and grew up in Canada, in Montreal, and I went to McGill University as an undergraduate.
Now, was geophysics and seismology, were those interests that you pursued during college?
Well, another great question. I had a very enlightened and enthusiastic high school science teacher, and he had I guess I was a sophomore or junior in high school, sophomore I think. He had us read an article written by geophysicists that was popularized in Atlantic Monthly magazine, and it had a lot of it was in the pre-plate tectonic era, but the ideas of plate tectonics and polar wandering and glaciations and grand ideas in earthquake science were all contained in this article, which mostly was wrong. But I thought, wow, this is wonderful. And from that age, I wanted to be a geophysicist.
Tell me about the opportunities that ultimately got you to Caltech. I pursued what was in Canada, and I guess English
England-related universities was called an honors degree, and it was joint honors in physics and geology. So I took all the math and physics that physics majors took, and then I took all the geology courses that geological scientists took, and kind of staggered through. It was a very heavy load, but I did well enough to be able to have my choice of grad schools, and I burned to be a geophysicist, and that was how I ultimately got to go to Caltech.
What other graduate school programs did you look at?
I applied to MIT and to Columbia University. I was accepted by all three. I was very attracted to California, and true story, you can include this in your oral history or not, but the Beach Boys were singing about California girls at that time, and that sounded pretty darn good to me.
Montreal's a pretty cold place.
Yeah, indeed, and the idea of long blonde-haired, bikini-clad California girls that the Beach Boys were singing about sounded pretty good to an impressionable and pretty innocent 20-year-old Canadian boy.
Wayne, what year did you arrive in Pasadena?
In 1965.
Now, the old Seismolab up in the hills was still in operation at that point.
Yes, and I'm glad that you raised the topic of the Seismolab, because one of my luckiest strokes in both my personal and scientific life was, first of all, to be accepted to go to grad school at Caltech and to be at the Seismolab. It was, for both of those things, it was a privilege. I feel lucky to this day that I was able to do that. The Seismolab was a very, very special place.
Wayne, when you were first arrived at Caltech, just administratively, how much of your time did you spend on campus at GPS, and how much of it were you up at the mansion?
Well, for the first year, I was on the campus just about all the time, because whatever our backgrounds in math and physics, Caltech usually deemed those as inappropriate to its standards. So I spent the first almost 2 years taking courses mostly in math and physics at the senior undergraduate level to bring myself up to speed. So all of the first year and part of my second year were spent on the Caltech campus. And thereafter, halfway through my second year, I passed my qualifying oral exams. And from that point on, I was at the Seismolab nearly all the time.
Wayne, just to paint the picture, who are some of the larger-than-life professors and visiting scholars at the Seismolab that stand out in your memory?
Well, first, let me give you a little bit of background to the atmosphere at the Seismolab, if I may,
Please.
To address your question. At that time, there were probably maybe like a half a dozen faculty members in seismology at the Seismolab. None of them was more than 10 years older than most of us graduate students. And so, and nearly all of them had gotten their PhDs at Caltech under the previous director of the Seismolab, Frank Press, who had left Caltech the year before I arrived. So they were all young guns, hotshots, bright, knew they were bright, but had the wisdom, probably because of the atmosphere under which they had been graduate students, to be very respectful and tolerant of the graduate students. And I think we all felt that we could express our ideas without fear of being judged or being wrong. And we usually were pretty taken by our ideas, and the faculty indulged us in that, what's the right word? Semi-fantasy, I suppose. And so we were made to feel very special in a way that definitely increased our self-confidence, made us bolder, made us work harder, made us be uber ambitious, for good or ill, and that was a wonderful aspect of the Seismolab at that time. Don Anderson was definitely the leading light. He soon after I arrived, I guess, he was ultimately named the director of the Seismolab. My own thesis advisor, Jim Brune, was a much quieter person, but also with a very strong ego and a scientific brilliance that certainly matched anyone at the Seismolab. And the other faculty were, again, very, they worked their asses off, they revered science, and they were, again, like everyone else at the lab, ultra ambitious.
Wayne, what were the big debates that animated the Seismolab when you first arrived?
So it was the winter and spring of 1967 when I started spending nearly all my time at the lab. And at that point, the rest of the geophysics world in the United States was largely convinced of plate tectonics. All the basic work had been done. The marine magnetic anomalies were identified. The process of seafloor spreading and subduction and the simplicity of the global plate motions was just beginning to be understood. And one of the leading researchers and contributors at that time was a young scientist named Dan McKenzie, who was from Cambridge University. He came and did a postdoc at Caltech just at that time. And so there was a lot of discussion and ferment about those ideas and how they applied to earthquake science. Most of the best and most original research was done elsewhere. I was totally captivated by the ideas of plate tectonics, in large part because I'd been exposed to them just the summer before I started at Caltech. I took a job in Ottawa at the Geological Survey of Canada, and there was a big international conference in Ottawa that summer that I attended. So, those were the big ideas that were being discussed. But seismology was in its infancy, and there was so many problems to attack that everything was exciting.
Wayne, of course, this is long before the internet and when data could flow freely across internet cables. To what extent was the data in possession at the Seismolab proprietary, or at least it was stuck in one place that compelled others from far and wide to come visit the Seismolab? That you stated accurately what the situation was. Very few people that I can remember availed themselves of that archive. In the early 1960s, before I came to Caltech or thought of being a seismologist, there was a major worldwide project called the Worldwide Standardized Seismic Network. And there were established roughly 80 stations, I think, around the world, later expanded, of these same seismograph systems. And they created a major impact on seismology. And that data was open and available to anyone who could buy the photographic film chips on which the seismographs were recorded. For my own research, the archive of Caltech seismograms turned out to be a gold mine. To this day, my most highly cited paper is one that I wrote with a fellow graduate student of Tom Hanks on using these old, very valuable seismograph records of large California painstakingly digitizing them and
basically determining the spectra of these earthquakes. And it was one of the serendipitous achievements of my career to be able to use those and take advantage of what at that point over 35 years worth of seismograms that Charles Richter and Benno Gutenberg had acquired.
Wait, I've heard it said, either because it's true or folklore, that the plate tectonic revolution largely passed by the Seismolab. I wonder if you can comment on that.
Oh, that's true. One of the downsides of feeling both the faculty and the graduates feeling as though we were God's chosen was that only ideas that originated at the Seismolab in Caltech were likely to be true, and plate tectonics was definitely invented, and the seminal research was done elsewhere. So there's certainly some truth to that. In my own case, my thesis advisor, Jim Brune, after 3 years at Caltech, accepted a position at UC San Diego at Scripps Institute of Oceanography. So I spent part of my time from 1968 onward at Scripps, and Scripps was one of the epicenters of the global plate tectonic revolution. So I was certainly exposed to those ideas more than probably any of the faculty at Caltech.
Wayne, what was the process by which Jim became your thesis advisor?
Oh, another great question. In those days, we were just accepted as grad students, and then we would start off at the lab, at the Seismolab, and we'd have a formal advisor, and I think Jim was my formal advisor, but we were basically set loose and told, learn about what's going on here, and we'll suggest a project for you, or come up with one yourself. And it was kind of by accident that Jim ended up being my thesis advisor. He was very hands off with his graduate students. He provided a little bit of guidance here and there, but I guess it was his own experience as a graduate student to be very independent. So he gave us a lot of independence, and so slowly the things I got interested in were things that made sense to work on with Jim. I was very personally impressed by him and by his integrity. He was and still is, a Quaker, so he was a pacifist. He was very active in the anti-Vietnam War movement, and I admired him personally tremendously. And that was kind of how it happened.
What were some of the big research questions that Jim was after when you connected with him?
He just wanted to understand earthquakes in general, and in particular what was written on seismograms. He had a very eclectic grad student career where, again, as I said, he had freedom to do pretty much what he wanted to do. And so one of his jobs, he was a grad student at Columbia University, was to be in charge of the seismogram record room at Lamont Observatory, where the seismology was done at Columbia. And so he just got very familiar with seismograms and the stuff that was on them. And he looked for pieces that didn't fit and then followed them up. It could be anything from the way in which seismic surface waves propagated to through the California crust and upper mantle to the details of the slippage that occurred on earthquake faults and how that got transmitted into seismograms. And So he was a very independent thinker, and that really definitely influenced the way that I approached seismology. He didn't parcel out, what's the right word, neatly constructed problems all pieced together for students to do as exercises. He threw general problems at us through conversation, and then it was kind of up to us to come up with particular research, well-defined research problems.
Wayne, his move to Scripps, was that more on a visitor basis, or was that a permanent move?
No, that was a permanent move, and it was basically. I told you the faculty were all young and ambitious and inquisitive, and when Frank Press left Caltech to go to MIT, he had been the director of the Seismo Lab and probably at that point the preeminent seismologist in America, if not the world. And so there was a big hole left. And the faculty that were hired at that time, they all kind of wanted to be Frank Press's successor. When Don Anderson shouldered his way into that job and was ultimately selected, and I think it was the right decision at that time. My thesis advisor and several other of the faculty decided they would look towards greener pastures to develop their career, and smart, acquisitive university departments like Scripps saw that and aggressively recruited him and lured him to La Jolla.
Now, as you said, the Scripps portion of the plate tectonic revolution, to what extent was that really the primary motivator in Jim's decision to join them?
Very little, actually. There, where the non-marine geophysicists hung out was a place called the Institute of Geophysics and Planetary Physics, and it was a separate building on the Scripps campus, situated like overhanging the ocean, about 100 feet above the sea. A marvelously built wooden structure designed by the wife of the then director of this institute, Walter Monk, and so it was where kind of the philosopher kings of geophysics would go and do their research, and that was the biggest draw, I think.
Wayne, what did this mean for you in the middle of your graduate study that Jim made this move?
It's one of the best things that happened, really. First of all, it made me more independent because Jim was at Scripps and I was in Pasadena.
So physically, you remained at Caltech.
Yeah, physically I remained at Caltech. Yeah, that's an important point. And but I had the best of both worlds. I would go down there kind of whenever I felt like it, and have an office or a bit of an office and interact with Jim and rub shoulders with all the luminaries in marine geophysics and plate tectonics. At that point, as I said, many of the main developments in plate tectonics were occurring at that time. Tanya Atwater was a grad student at Scripps at the time, a wonderful scientist and woman. She's still a dear friend of mine. And half a dozen other marine scientists that I felt lucky to be able to interact with.
Wayne, with direct perspective on two great institutions of seismology as a graduate student, do you think that affected your thesis research in any way?
No, not my thesis research, because by the time Jim had moved, I was his student. I was doing problems that were more closely related to his research and his interests, and The course I followed was basically taking his lead. One of the great papers in seismology, Brune 1970, was written soon after Jim moved to Scripps. It influenced a lot of my subsequent research. The work I did with Tom Hanks that produced Thatcher and Hanks 1973 was a direct consequence of Jim's influence. So it was Jim that influenced me primarily, not Scripps.
You mentioned how hands-off he was. Tell me about the process of developing the main topic of your thesis and what role Jim played in that.
Well, first of all, in those days at the Seismolab, and I think generally for others in seismology at least, my thesis topic, it wasn't one topic. My PhD thesis, when I ultimately finished it in 1970, spring of 71, was basically 4 scientific papers put together in under one cover, and one was on the first problem that Jim Brune had set me. A second was a question that arose about seismic surface waves that a theoretical problem that together with Jim we solved. A third was related to this Brune 1970 paper, and a fourth was there was a big swarm of large earthquakes, or moderate earthquakes as large as magnitude 6.5 in the northern Gulf of California that occurred at the time that I was a grad student in early 1969. And so that was the thesis project. It was really 4 different projects.
What do you see as some of the connecting threads between the 4 papers?
Well, the seafloor spreading in the Gulf of California, I guess, would be a single unifying theme. The 3 studies were all in, except for the theoretical one, were really had their roots in understanding earthquakes in Baja California, in the Gulf of California, and the structure of the crust and upper mantle under those regions.
Who else was on your thesis committee besides Jim?
Oh, that's a good question. Well, one was Barclay Cam, and I don't know if you have a picture in your mind of Barclay Cam.
I certainly do.
Okay, so you probably know Barclay was a genius.
Yes,
and he spanned everything from quantum chemistry to geologic fieldwork, but really the whole range. And excuse my French, all of us graduate students were nearly always scared shitless of him. And to my horror, he was on my PhD committee. And the others, I of course Jim Brune, and I think there were Don Hellenberger was on the faculty then, so I think he must have been on my committee. I'm not sure whether Don Anderson was or not, and probably Dave Harkrider. Hiro Kanamori hadn't yet arrived at Caltech, so I think that was pretty much my thesis committee.
When going back to the idea of boldness in youth, either then or retrospectively looking back now, what do you see as your contributions to the field up to that point?
Up until what point? I'm sorry.
The point at which you graduated from Caltech, defending the thesis.
Oh, my contributions? I would say, in the larger context, minor, to be honest. They each of them made a little splash at the time, not least because I was at Caltech, not least because I was very, what's the right word, proactive in promoting my ideas, and I was seen as bright and promising. But those particular pieces of work, that they didn't. There's nothing very enduring in any of them.
Wayne, what opportunities were available to you after you defended? What did you want to do next?
Well, this again is a very personal note. My girlfriend at that time, and subsequently my wife, had graduated from UCLA in the spring of 1969. So she moved, and then she was born and grew up in LA. She couldn't get away from Los Angeles and her parents fast enough, so she moved up to Berkeley, and she was a very free-spirited hippie girl that I loved deeply. So one of the reasons I went and joined the U.S. Geological Survey here in the Bay Area was because Mary Ellen was in Berkeley, and we subsequently, a few years later, got married and had a wonderful life together. She died about 10 years ago. She got ovarian cancer. So I'm not sure if I've answered your question.
When did the USGS come on your radar?
Well, I was still a graduate student. The USGS was and is places emphasis on observations, and in particular making new observations and making long-term dedicated observations, establishing networks for seismographs, for geodesy, for various kinds of geophysical measurements. And my professor, Jim, was the preeminent and certainly the brightest young star in observational seismology at the time. So as his student, I was seen as a pretty hot commodity. And while I was a grad student, one of the seismologists at the USGS basically invited me to come up and work together with him on a project that was related to, in a general way, to my thesis research. And he and another colleague were the ones who recruited me most vigorously, made me feel wanted, and ultimately that was why I went to the USGS after I got my PhD.
In reflecting on your ability at the USGS to pursue topics that were interesting to you, did you understand that going in, that there was a strong academic culture?
Yeah, I was not browbeaten by anybody to, well, there's one exception, I guess, but largely told or given the impression that I should do what I found interesting and exciting. I was hired to basically follow on research on measuring and understanding the spectra of earthquakes, basically the impact of this Brune 1970 paper that I referred to you to. After a couple of years, I got interested in the 1906 earthquake and geodetic measurements related to it, and abandoned seismology. And in retrospect, it was probably a pretty brash thing to do at the time, because I had no guarantee that this research would turn out to be as important as it ultimately turned out to be. But I was self-confident. I thought I knew what was important, and in that instance, I was certainly correct. And just by osmosis, being among scientists who did appreciate and value the dual role of the USGS as both pursuing curiosity-driven science, but in the service of bringing better understanding of earth science and its importance, and earthquakes and its importance to society in the United States, that began to sink in.
Did you feel like you were academic adjacent at the USGS, that you were essentially a professor working for the government?
Well, it was even better than working as a professor for the government because, by and large, the research that I was doing was not expensive at that time. Didn't involve any field work. I had total freedom to pursue what I was passionate about. I had no administrative responsibilities. I didn't have to teach. I didn't have to direct a scientist, and I didn't have to scramble for funding by writing half a dozen proposals to NSF each year to get one or two of them funded. So it was better than being a professor.
That sounds like the complete package, actually.
It was, and the USGS has changed over the decades, as universities have changed over the decades. However, when we hire young scientists, it's often a little bit more directed towards particular problems or particular programs. But I like to make sure that they feel, those that I have any influence over, to feel like they should follow their passionate interests and worry less about how they might programmatically fit in. And if they're good and they're good scientists, then they will flourish and prosper at the USGS.
Wayne, for the last part of our talk, I'd like to ask a few broadly retrospective questions, and then we'll end looking to the future. So first,
Sure.
Have you remained connected with the Seismolab over the year? Are you what we might call an active alumnus?
No, I wouldn't call myself an active alumnus, but as I'm sure you've gathered, I have great affection for the Seismolab and a real gratitude for my experience there. In 1998, excuse me, so more than 25 years after I graduated, I was invited back to be a visiting professor, which was a lovely experience. By that point, the Seismolab, to the degree that it was distinctive, was just a part of the South Mud building. But some of the atmosphere that I had felt was still preserved. The Seismolab coffee break, which was a very precious institution at the old lab, was still preserved. Don Anderson and Hiro Kanamori would nearly always attend the Seismolab coffee break. And so I felt at that point a very strong connection reignited with the Seismolab during the 4 or 5 months that I spent there.
Wayne, beyond the all-important preservation of the coffee break from the old Seismolab, what was lost and what was preserved when it moved back to main campus?
Great question. What was lost was that the really wonderful camaraderie that existed at the old lab. There was only, I guess, probably no more than half a dozen PhD grad students at the time. Usually there were 3 or 4 postdocs. Often they would just come for a year and then move on to some academic position or other, and then half a dozen faculty or so. We were our own world. We were a community, I guess here's a 21st century word. We were a community, and community is very precious, and that's what we were, and that could never be recreated, in my view, and was not in the move. An advantage, earthquake science, like most science, certainly earthquake science and geological science is much more multidisciplinary now than it was when I was a graduate student. And one of the reasons why the Seismolab moved to campus was Clarence Allen's vision that geology and seismology should be, like earthquake geology and seismology should be integrated, and that was one of the rationales, and I think a good one. Many, if not most, of the Caltech faculty now are definitely more multidisciplinary than those that were at the Seismolab at that time. Although that said, my thesis advisor and certainly Don Anderson were as multidisciplinary as any at that time.
Wayne, however one measures these things, do you still see the Seismolab as being central to the most important research happening in seismology?
Absolutely, sure. Caltech has always been able to attract, cliche, the best and the brightest, inculcate them into the Caltech culture, a bit elitist, but the Caltech faculty are the elite, and dedicate themselves, pretty fully and completely, body and soul, to the pursuit of knowledge, and that's a very valuable and precious thing in our society, in my view.
Wayne, either in interactions with individuals or just absorbing the overall research culture of the Seismolab, what has stayed with you over the course of your career that you learned at Caltech in terms of how to pursue the research, how to frame the questions?
I think the most important in that context is I try to frame my research projects in the broadest possible context. And at that point, and still, plate tectonics is kind of the largest context. And certainly in everything that I've done since then, that has been an important element. I'm not a technical specialist for the most part. I have made technical contributions, but my research is problem driven rather than technique driven. If I have a problem in mind and there's a new technology like GPS or satellite radar interferometry, which we haven't gotten to talk about, then I will do my research from a problem-oriented point of view, and that's I think something that I learned at Caltech.
Wayne, what about the culture of science? In other words, learning to collaborate with others, choosing who your research partners will be. What did you learn in that regard from the Seismolab?
The Caltech research environment at the Seismolab, I would say on the downside, was very selfish. It was kind of a me first, I'm going to make these discoveries, rather than let's work together and build on our collaborative skills to make the whole better than the sum of its parts. That part I learned at the USGS. USGS is very, at that time and still is very multidisciplinary in its pursuit of earthquake science, and that's something that I learned to value. Well, probably the 5 years I was a scientific administrator, and which is it's the way that I choose to be as a scientist and kind of as a person as well. And I didn't really get that at Caltech.
Wayne, in reviewing your research career and all of your contributions, whether you source them directly in your education at the Seismolab or not, what are you most proud of in terms of impact or in terms of discovery?
Let me answer it this way. The times that I've been most excited by science have been in the research I did soon after my PhD on the 1906 San Francisco earthquake, and then where it led for roughly the next decade. And then with the advent of the global positioning system, my research turned towards less on earthquakes in particular, to how active regions of the globe, the continents, how they deform broadly, with the folding and faulting and the earthquake occurrence and the creation of the topography, in particular in the western United States, where my GPS research was spread for 25 years. Those have been the areas that I've been most excited about. And in terms of what I think my contributions have been, one has been to understanding this earthquake cycle of strain accumulation and release that is clarified by geodetic measurements on the one hand, and then how the continents deform in a kind of a mini plate tectonic kind of way, rigid blocks rotating around and interacting with each other. I think those areas have been most exciting to me, the largest broad fields I've worked in, and where I think I've made some useful contributions.
Wayne, to flip the question around, looking back at your career, do you see any misses, any research areas that you spent a lot of time on that ultimately led nowhere?
Oh yeah, not big things, but I'm the kind of person that is driven by my enthusiasms, whether they're scientific or personal. And sometimes my scientific enthusiasms were misplaced. And in that context, I've been cleaning out my old office at the USGS. We moved campuses just before COVID, and I'm now actually emptying out my old office, and I'm going through all of the papers pieces of paper and computer output and everything that I've collected, kind of like a pack rat, since then, and I've seen, oh yeah, here are 3 or 4 files, thick files of something that I worked on with great interest and enthusiasm that in the end turned out not to result in a published paper, or I published a paper that I thought a lot of at the time, but it didn't amount to a hill of beans in the larger context. So yeah, I've followed a lot of alleys that have led either nowhere or less productively than otherwise. But that's part of the freedom of being a government scientist, in that I didn't need to feel like I had to turn out 6 papers a year in order to have the esteem of my academic colleagues, or be sure to get research grants. I followed what my interests were, and if they didn't work out, I'd take my lumps and move on to another project.
Wayne, finally, 2 last questions looking to the future. In your capacity to interact with younger scholars in the field, what do you see as some of the most exciting developments and possibility that might suggest where things are headed?
Ooh, that's another really good question. I think being basically an observationalist, I think that observations will trump theory in Earth science every time, pretty much. Mm-hmm. And so the development of new observational networks and new computational techniques, for example, because computers are always getting stronger. Those are the areas where the biggest advances can be made. And drawing on my own career experience, awareness of new technology and taking advantage of that to solve specific problems, that's what I advise my younger colleagues to do. In my own specialty, the development of seafloor geodesy, so seafloor GPS measurements, essentially, is beginning to make an impact, and over the next decade or 2 is going to make a larger and larger impact. The same is true of ocean bottom observations of all kinds, for example, around subduction zones where these megathrusts exist. I think will also have a large impact. So those are some of the areas where I think young scientists will find and move on to. A lot of it is just really kind of unknown, and the fun of science for me has been to opportunistically take advantage of new measurements or new ideas to put a few more bricks in the wall, or maybe even start constructing a new wall in science.
Finally, Wayne, for you, for however long you want to remain active in the field, what do you want to accomplish that you haven't yet?
Nothing. I've been very lucky in my scientific career to be able to do research mostly in following my own curiosity. I've accomplished more than I think I would have imagined when I was a graduate student, and I've had a wonderfully fulfilled life. I continue to interact with my colleagues. I formally retired in 2015, so that's 7 years ago. I still love to continue and keep my hand in science, but I don't have any aspirations other than to keep my hand in, enjoy what the developments that occur, be totally supportive and applaud my colleagues of all ages when they achieve something, and live the rest of my life as a good person, I guess.
Wayne, on that note, this has been a terrific conversation. I'm so glad we connected to capture your insights and perspectives over the course of your career. Thank you so much.
Thank you. It's been a wonderful experience, David.